Hello, this is part 4 of controlling a non-integrating first order system. Basically, it is a motor system in velocity mode. So we have the first order system here, and the gain. It's just like a low pass filter with a gain. And today I want to talk about direct synthesis, another way of calculating gains other than using pole placement. I also want to talk about sample time, and I want to talk about having the proportional gain being used as acting on the error or acting on just the change in the actual velocity. So first I'm going to start off with the calculating of the gains using direct synthesis. And so to start with, again, I have my open loop model for the motor and load. This is the PI controller. And the closed loop transfer function, again, is in this form. And I need to do substitutions. So I substitute the controller gain here and here, and the open loop model here and here. And I simplify that. So now the closed loop transfer function is this. I can now solve for my controller gains. I have to remove the S because it doesn't solve for functions itself, just variables. So the controller transfer function is this. And if I then substitute the transfer function, the open loop transfer function for the motor, and the desired transfer function, which is just a single pole, like a low pass filter, for my desired closed loop transfer function, and then solve, I end up with this. So this is my proportional gain, symbolic proportional gain, and this is my integrator gain, and I can tell which one is which by where the S's are. And the gain itself is just the coefficients without the S. So I'm going to now assign numeric values. I'm going to start out with something very simple. I'm going to just assume that the motor's got a gain of 10 millimeters per second per percent control output. So the top speed is 1,000 millimeters per second at 100% control output, or 1 meter per second. I'm going to assume that the motor's got a bandwidth of 20 hertz, and so the magnitude is down 3 dB, and phase lag is 45 degrees at 20 hertz. Now, there's two real poles, and what's going to happen with the direct synthesis is that it places one of the zeros on top of the poles. So it'll cancel out one pole and it'll leave just the remaining pole, but there are two real poles, and they're going to be placed at minus lambda. And so this is a good place to start for gains, because I'm not pushing the system too hard when I set the closed loop pole to be the same as the open loop poles. Anyway, using the formulas from above, I can calculate the integrator gain and the proportional gain. And so I have these two values here, and that's what I'm going to use for now. I'm going to change the gains later. I have controller updates. This is the controller update rate in seconds. Right now I'm going to assume the controller update rate is 1 millisecond. That's a pretty good rate for most applications, but we'll see that for really fast responses, it's not fast enough, and we're going to have to try using a 1/4 millisecond, but that's later. And then am calculating out the gains for the low pass filter. This is the open loop transfer function implemented in a digital form. So it's like a low pass filter with a gain. Got my initial values. Now, I'm going to take a small detour and talk about the proportional gain and whether or not the proportional gain should be used in the forward path or the feedback path only. And I will explain how you implement each case. First, I want to talk about the PI controller. And the PI controller, notice that the controller gains, all the controller gains are in the numerator and the denominator. In the I minus P controller, only the integrators in the forward path, and the integrator and the proportional gain are in the feedback path. So what this means is the integrator gain and the proportional gain act on the target, the difference between the target and the feedback, or the set point in the process variable if you're a process guy. In this case, only the integrator gain is acting on the error between the target velocity and the actual velocity, and the proportional gain is only acting on changes in the actual velocity. So the big difference is that the PI controller, because it's got the two gains in the forward path, it introduces a zero, and the zero will cancel out one of the poles, so I am left with a time response that looks like this. This is using the values from above. So I have 1, which is my forcing function here. This is the forcing function, and the system should respond by getting to 1 in some time in the future. And as the t gets bigger, this decays down to 0, so we're just left with 1. In the I minus P controller case, it's basically the same thing, except for we have 2 poles, and but they both decay and go to 1. Now, another thing I want to point out that we're going to see later when we're talking about sample time is that you can see that this should never overshoot 1 on the velocity, because there are no positive terms here in the transient. This is can never add to a number that's greater than 1. And the same down here. These are all negative terms. So this these terms should never be greater than 1. So the velocity response should never overshoot the target velocity. And I'm going to get to that later when we're talking about sample time. So now I'm implementing the PI controller, and this is taking the velocity and the control output and calculating the new velocity. This is the error between the target and actual velocity, and we're multiplying the proportional gain by the error to get the proportional term, and then we're multiplying the Ki times T times the error to update, and then adding it to the old integrator term to get the new one. I sum the two together and I return the new velocity, new control output, and the new integrator term. It's very simple. The target generator is very simple also. I'm doing step changes to plus and minus 200 millimeters per second, and I'm ending up at a minus 100 millimeters per second. So I'm calculating the target velocities here. And I do this because one, it's simple, and two, is it introduces a lot of frequencies to the motion, and you can really test to see if your control algorithm is going to work the way you want it to at all frequencies when you use a step. So, as predicted, the target velocity goes up to 200 millimeters per second, and the actual velocity goes up to 200 millimeters per second. It doesn't overshoot, just as predicted. It takes it about 0.35 seconds, 35 milliseconds to get to the target. You can see the change to 200 and minus 200 minus 100. Going to step down a bit and look at the sine wave. Now let's just see here. This is going to become a little bit more important later. This is the I minus P control. This is identical to what was done up above, except for now the proportional term only acts on the velocity, actual velocity, and then we still return a new velocity, new control output, and the new integrator term. But you can see that because there's no zero in this system, it doesn't can't cancel out the poles or one of the poles, so the response is much slower. It takes almost a whole 50 milliseconds to get to the target velocity of 200 millimeters per second. You can look at the sine wave. We can also see the sine wave has got a little bit more attenuated and a little bit more phase lag. So let's go down and take a look at the Bode plot. And I've plotted out two sets of values, one for the PI control and one for the I minus P control. This is the PI control, and you can see that its magnitude stays a little bit higher as frequency increases, and the phase lag isn't as much when you get to the higher frequencies. And the reason why is because, again, the PI controller has a zero which cancels out one of the poles. So there's only one pole left, and you're left with a phase lag of at most minus 90 degrees. And this will attenuate at just like a single pole low-pass filter. The I minus P has two poles, so one is the phase lag is going to approach minus 180 degrees, and you can see that the attenuation is double the rate for the single pole filter. Now this is 20 dBs per decade, this should be 40 dBs per decade. Let's look at the pole zero plot. And because I set lambda, the desired closed loop pole, to be the same as the the pole to be the same as the open loop pole, we have two poles now at well, this is 20 hertz. And what happens is the direct synthesis puts 1 0 at 20 hertz. And so what's happening here is we have two poles and 1 0 here at basically 20 hertz, or minus 125.6 radians per second. So now let's go back and see what happens when we change the frequency response. We want to make a faster frequency response, and so what we'll do is we'll go back up and let's make our desired closed loop pole at 2 times the open loop pole. And now I need to go all the way back down. And you see that this is the new value of lambda, and you can see that it moved out to a double the 125.6. So it's out here. And again, the direct synthesis cancels out the original pole, which is the open loop pole. And so we're just left with this one pole at minus 251 radians per second. So let's look at the response. See if I can get there quickly. You can see that the response is much faster, and it still doesn't overshoot. So that's excellent. Of course, it shouldn't overshoot in theory. Let's look at the sine wave, and you can see that there's hardly any attenuation in the magnitude, and the phase lag is not quite so great as before. I minus P, you can see that it's a lot faster. The last time when the closed loop pole was set to minus 20, or at 20 at 20 hertz, then what happened is that it took almost a whole 50 milliseconds to get to the velocity set point, and now it's about 40 milliseconds or so. So let's try increasing the bandwidth a little bit more. This is where the controller really starts to pay for itself. So let's make this a 4. So now the closed loop pole should be at 500 and something, and there still will be an open loop pole which gets canceled out by a 0. So we're going to just be left with a closed loop transfer function with one pole at about minus 500 radians per second. So let's take a look. And notice that it's overshooting. Notice also that we, from the formulas above, it shouldn't overshoot. The response is going to, this number has gotten more negative, but still this whole number here is going to be negative, so it should never overshoot 1. So what is happening? Basically what is happening is the sample rate isn't fast enough to make this kind of move without overshooting. And you can see that we're saturating here, and we're almost saturating here too. So let's see what happens if I increase the sample rate. I'm going to disable 1 millisecond and enable 250 microseconds, and that changes these coefficients here. But basically I'm sampling at 4 kilohertz instead of 1. These formulas don't change. This hasn't changed except for the integrator here. That time is changed. And you can see that the closed loop response moves very, very quickly up to the target velocity, and there's no overshoot. So basically what this is saying is that for most applications, you can probably get by with a 1 millisecond sample time. Even if we didn't have 4 kilohertz sample rate, and I enable this again and disable this, as long as you're moving with at a slower target velocities, you see like in this sine wave, you won't have any overshoot, you won't have any problems. So basically the rate of change in your target generator is going to determine the kind of sample frequencies that you need. So for instance, a conveyor line that's always going at a constant velocity, it doesn't need to have a very high sample rate. But if you're spinning up something very quickly and then stopping very quickly, where the accelerations are very high, and the frequency components to your target profile is high, you're going to need to have a high sample rate. One other item that I'd like to point out is that properly implemented PID or PI should have the Ki gain multiplied by the sample time. And the reason for this is that if you don't have the sample time integrated here, if I were to close the loop 4,000 times a second, excuse me, what would happen is that you would add the integrator gain 4 times too fast. But since this number gets smaller, it compensates for the fact that it's sampling more often. And that makes it so that the response should always be the same. You don't need to change the integrator gains. So basically, one more thing I'd like to be able to do here is go on down here and show you the pole 0 plot. So this is the pole that the direct synthesis, this is the open loop pole, and the direct synthesis has moved a 0 over that pole. And then this is the minus lambda, so we're at minus about 505 radians per second, I think, 502. So that is why this response is very, very fast. And there's no overshooting, or in theory there's no overshooting, because there are no complex components to the poles. So I hope you found this interesting. Covered quite a few topics very, very quickly here. So till next time, bye.